Alright, hello everybody, and welcome back to Kareem's Chemistry Corner. Oh yeah. So we're back with some PV equals nRT problems. First one being number of molecules occupying a chamber. Second one being molecular weight of a gas that occupies a certain volume, certain pressure, at a certain temperature, and has a certain weight. So we can figure out what the molecular weight of that type of gas is. This might not be a problem you've been exposed to before because I haven't really seen it that many times, but it's good to get in the habit of being able to use that equation in all different ways. Okay, so let's start with this one since it's a little bit more simple, and that is how many molecules of hydrogen occupy this 3.3 liter chamber that's at 5.6 atmospheres and 22 degrees Celsius. Okay, so this is obviously a gas problem, right? Because H2 is a gas. But also we have a volume, pressure, and a temperature. So that should be a pretty dead giveaway about that. And so for gases, we use the ideal gas law, which is PV equals nRT. R is the universal gas constant. So that is 0.08206 liter atmospheres per mole Kelvin. There also is a one in joules, but we're not going to use that one today because I'm not using, I think that one's in joules per mole Kelvin. And this one has atmospheres, so that's why I'm using this in particular, because we have atmospheres, we want the R that has atmospheres in it. So R equals 0.08206 liter atmospheres per mole Kelvin. Okay. Our 22 degrees Celsius needs to be converted to Kelvin first, so that will be 295 Kelvin. Because remember that T has to be in Kelvin. If you have negative Celsius in this equation, then it will ruin everything. So just keep that in mind. If T's in Celsius, you could have a negative number here. So you could end up with like negative or positive moles. That is weird. So T is in Kelvin, absolute measure of heat, or of temperature rather, excuse me. So we have our P, which is 5.6 atmospheres. We have our V, that is 3.3 liters. We don't have N, that's what we're solving for. We have R, that's 0.08206 liter atmospheres per mole Kelvin, and I've run out of space down here, but this is 295 Kelvin. Okay, so this is being all multiplied together. And so if we multiply all of this together, we can multiply these two together. So if we multiply 295 by 0.08206, we end up with 24.21. So that's going to be 24.21. Now we've multiplied by Kelvin over Kelvin, so the Kelvins would cancel. And so then that would be in liter atmospheres per mole. Okay, since we just got rid of that Kelvin. And then we still have N. And we still have our 3.3 liters, and we also still have our 5.6 atmospheres over here. Okay, so we have everything that we need right now. If we divide by liters, so let's do that. Divide by 3.3, we're going to lose that liter. And then if we divide by atmospheres, we're going to lose that. And so we're going to basically end up with N times something 1 over moles. Okay? And so then if N is times something what's 1 over moles, then you bring it over to the other side, then you end up in moles, which is what N should be in. So what I'm actually going to do is divide 5.6 and 3.3 by this 24.21 right here. So let's do 5.6 times 3.3, and then let's divide that just by using the answer feature there. 2, 1, okay. So now we have our value right there, which is 0.76. My calculator isn't scientific. So that's going to be, yeah. And it's going to equal 0.76 moles. Okay, but that's not what we're asking. We're asking how many molecules are there. This is moles. So for us to convert between molecules and moles, we do 0.76 moles times Avogadro's number, 6.02 times 10 to the 23rd. And this would have to be in particles per mole. Okay. Just so that way you end up with particles at the end. So we take this, multiply that by 6.02 times 10 to the 23rd. Let me just make sure I plug it in correctly. Yes. Okay, so then we end up with 4.6 times 10 to the how many? 23. Particles. Okay. And so that is how you find out how many molecules are occupying a certain chamber. Convert to moles first, and then convert to particles. Okay. So let's get rid of this. So I have my PV equals nRT there, and so let's move on to our next problem. So our next problem is this. What is the molecular weight of a gas that at 300 Kelvin occupies 0.5 liters, 0.5 atmospheres, and weighs 0.28 grams? So it's a lot of information about this gas, but that is going to be plenty of information for us to be able to solve this problem. Okay, so again, we need PV equals nRT, as you're probably not surprised to hear. And then R, again, we're in atmospheres, so R is still going to be that 0.08206 or 8205, that's whatever, liter atmospheres per mole Kelvin. Okay, so it's still going to be the same R. Your R will be 8.314 joules per mole Kelvin if you're using different pressure units, okay? So, or volume units too, but that would be a really bad idea. I don't know why you would do that. Okay, so if we have our P, we have our V, we have our T, we also have our R. So we don't have N, but we have the weight of that gas. So the thing that we're going to do is we're going to use PV equals nRT to find N, and then once we have moles, we're going to actually divide. How do I want to say this? We want to divide this number by the number of moles that we end up with to give us our molecular weight, right? Because molecular weight is in grams per mole. So we're going to find those moles, divide these grams by those moles that we find. So 0.5 liters, or I guess 0.5 atmospheres for P, 0.5 liters for V, N we don't know, 0.08206 liter atmospheres per mole Kelvin. And again, the units do need to cancel, so make sure that happens. And we have it in Kelvin this time, so we're just going to put T in there. And now we can solve for N. Okay, so I will do that. So if we take 0.5, multiply it by 0.5, that gives us 0.25 for this side. Then we're going to divide it by this number, and then divide it by that number. So then we're going to divide by 0.08206, and then we're also going to divide by 300. So we're just isolating N, just some basic algebra. 0.01 looks like. Point has a small number, 0.01. Let me move this over here. So N equals 0.0102, I guess, if we want to really push it. Moles. Sig figs are not accounted for right now, but we'll do that at the end. So obviously we're going to have one sig fig, because we only have one sig fig in those top answers, including 300 too. So we have our N, we have our moles, and we also have our weight. So let's divide this by 0.28 grams. Divide by 0.28. Oops, I have not done that. 228. A lot of glare on this screen here. Oh, sorry, we need to divide 0.28 by 0.102. So what I've done here is this is moles per gram, so we actually don't want this. What we actually want is 0.28 grams on top. Like I said earlier too, I mean I said grams per molar earlier, so I wasn't joking around about that. So 0.28 times, or divided by 0.102. Okay, so then we get about 28. So because we're only at one sig fig, I'm actually just going to leave it at 28. Also, this 2 is not really that like significant either way. So about 28 grams per mole. That's the molecular weight of our unknown gas. Now, if you look at your periodic table, there are some gases that could be 28 grams per mole. But the solution to this problem, or at least the gas that I was thinking of, was a gas that is diatomic, which is N2. and that would be 14 grams per mole for each of those nitrogens. So then that would be times 2, and that would give you 28 total. Okay, so that's how you find the molecular weight of the gas based on some information, and then also how you can use the equation to determine, oh, I put it away, to determine particles. Okay, so hopefully that was helpful. You can let me know if you have any questions, and good luck. I will see you next time.